Hello and welcome to the following series of video presentations covering the Catapult Design Analyzer. In this series of video modules, we will cover an introduction to Design Analyzer, using the Design Advisor for advanced analysis, analyzing multi-block designs including reporting such as bill of materials and resource sharing, and we'll finish up with doing failed schedule analysis. High-level synthesis automates the creation of RTL from C++ or SystemC. Typically, parallelism and concurrency are added using design constraints. It is often hard to understand the relationship between the C++ and the synthesized RTL. Looking at the RTL schematic, as we see on the right, typically results in a sea of gates where it is hard to determine how the C code combined with constraints resulted in the created hardware. Even experienced designers often struggle to analyze and optimize their designs. They often don't know what to do when things go wrong, or why is the area so big? Why won't the design schedule? Why is the runtime so long? The Catapult Design Analyzer provides designers with the ability to understand and see how high-level synthesis has synthesized the design. Design Analyzer allows you to analyze the effects of C++ coding style combined with design constraints and understand how the underlying hardware was created. It also gives designers the ability to quickly pinpoint problem areas in the design and provides recommendations for recoding. And lastly, it provides debug views for the worst possible synthesis errors such as failed schedule errors. We will begin with a very simple example that shows how Design Analyzer works. For this series of videos, we will be using the Catapult 10.5 beta build along with the 10.5 release of Design Analyzer. Some of the features shown in these videos are not available in the 10.4 release of Design Analyzer, but most of the functionality is the same between the two tools. In this very simple example, our top-level design is a C function that has AC channel streaming interfaces for both the inputs and the outputs. The input data and weights are packed using AC array with 8 elements being sent in parallel. The array data is read from the channel into some local variables, and then we perform a multiply accumulate of the data against the weights and write the data out to the output channel interface. We will target the NAND gate 45 nanometer sample library, and we'll set the clock frequency to 1 gigahertz. The design interfaces default to CCS in weight and CCS out weight for our AC channel streaming interfaces, and we will pipeline the entire design with an initiation interval of 1, and we'll leave the processing loop for the design rolled so that the multiply adds are performed one at a time. Let's generate RTL for our design. Design Analyzer can be launched directly from the Catapult GUI or at the command line to be run in a standalone fashion on any Catapult project. We launch Design Analyzer by double-clicking on the icon in the Catapult GUI. The first time Design Analyzer launches, it will display the design using the default perspective. This perspective consists of the following. It consists of the modules and scopes window that shows us the design blocks in our design. In this case, there is a single design block. Provides details about the modules such as the ports on the design, and provides information about the various scopes in the design, such as the loops as well as function calls. The RTL schematic shows us the synthesized hardware. The object view provides information about the various objects used to build the design. The text editor view shows us our design sources. And the schedule view shows us how the various operations in the algorithm have been scheduled over time. All of the views in Design Analyzer are connected to the same underlying database, and clicking anywhere in any given view will automatically highlight data in another one of the views. This makes Design Analyzer very useful for navigating the design and understanding how the C code relates to the hardware. Starting with the Modules and Scopes view, we can click through the module details for ports and immediately see that as I click through the ports, they're being highlighted in the C code, as well as sections of the RTL schematic are being selected, showing us the design interfaces that were created using interface synthesis. Similarly, I can click through the RTL schematic and notice how the other views update, highlighting various sections of the C code. So here I click on this red circle, which is a hardware multiplier, and we can see that the star in the C code is being highlighted, as well as the multiplier in the scheduled design. Also note that the object view has selected the multiplier in the list of operations and provides detailed information about the selected object, in this case, a multiplier with two 10-bit inputs and a 20-bit output. The default state for the object view is the allocate state, which matches what we see in the schedule view of the design. So the object view by default is showing us all of the operations that were used to schedule the design. However, this does not account for resource sharing, and the actual hardware is shown in the extract state. So if I want to get detailed information about the actual hardware that was used to create the design, I can switch the object view state to extract. For this example, it doesn't make much of a difference. Let's start looking at some of the more advanced things we can do with Design Analyzer. But before we begin, it is worth mentioning that Design Analyzer has been built to be highly intuitive as well as helpful. You will notice that there are many buttons that we have not discussed yet, but hovering over any button or icon in the Design Analyzer will give you an explanation or more detailed information about the functionality of that button. Furthermore, there is an interactive help menu that is tied to the particular view that is selected and gives you more detailed information about the view and its buttons. So here we can see, because I've clicked in the schedule view, that I get help about scheduling. Clicking in the schematic gives me help about the schematic, and so on and so forth. By default, when Design Analyzer launches, it selects the top-level design and places that in the Design Analyzer filter. This can also be done by clicking on the appropriate button in the toolbar. For a multi-block design, it would be selected and we would see the design blocks in the schematic. When objects are added to the design filter, the Modules and Scopes window indicates this by highlighting the filtered items in yellow. Because our example is a single block design, the entire design has been added to the filter, and we see the entire design displayed in the RTL schematic. In a more complex design with more operations and more code, it would not be obvious about how the schematic relates to the structure of the C code, and Design Analyzer allows us to filter the design to look at specific areas of the design. The scope view allows us to select, highlight, and filter the various scopes in a design, which can consist of loops, function calls, or conditions. By selecting a scope and filtering, Design Analyzer will display just the section of the design related to that scope and that section of C code. In this case, just the for loop that does the 8 multiply accumulates. So clicking on the filter button, we can see now that we have reduced the amount of objects that we were viewing compared to the top level design. Likewise, any section of C code can be selected in the text editor and filtered to that selection. Notice how the yellow bar, which is our filter, now is set just for line 15 of our design. The multiply is highlighted in green, indicating that I'm selecting it. And the RTL schematic now shows our hardware multiplier along with some additional operations that are linked to this multiplier. More objects can be added to the filter by selecting the readers or the writers of the current selection and adding that to the filter. There are 2 buttons in the toolbar that allow me to navigate forwards and backwards through cones of logic in the RTL schematic. So for example, selecting the multiplier and finding all the readers of that multiplier, we then have the D-flop that the multiplier feeds, and searching forward again, that D-flop feeds an adder. This is where we start to see the real usefulness of Design Analyzer, because I can now see how my multiply add from the loop in my C design has been scheduled, where the first multiplier was scheduled in C1 and the add that it feeds is scheduled in C2. And by crossing a C-step boundary, this implies that a register has been inserted, and we can clearly see this in the RTL schematic. In navigating and filtering the design in Design Analyzer, it can be seen that as the filter is applied, the windows are updating to show just the objects that have been filtered to the current selection. While this is very useful, it may also be desirable to lock down certain views within Design Analyzer as we are filtering to a selection. Many of the views in Design Analyzer can be locked to the current selection. So going back to the top level design now, we can take the schematic view and we can lock the content to the current filtered selection. And now we can begin filtering within the scopes or the C code view. And now, instead of removing objects from the RTL schematic which we have locked, we can see that it's simply highlighting the filtered selection while filtering the other views. So further filtering onto the multiplier now, we see that our schedule has been filtered to just the multiplier being fed by a mux input, and the schematic is simply highlighting that same selection. There are other useful things to be done with the schematic. For example, I can switch it to a gray view, which shows only the selected items in color with all other objects being grayed out. Catapult Design Analyzer has many other views and windows that can be useful in analyzing the design. However, the default perspective or default view is designed to minimize clutter, and Catapult provides a number of built-in perspectives that can be switched to for viewing the data in a different manner. We will go through these different perspectives in some of the later video modules. Along with the perspectives, which use many of these other views and windows, we can also simply select other windows and add them to the current perspective. So for example, I can add in the Files widget that gives me all of the design files as well as the output files, such as the Verilog or the VHDL. One of the challenges in the past has been trying to understand how the synthesized RTL relates to the C code, and Catapult Design Analyzer not only links all of the different views such as RTL schematic, object, and C source code together, but it also provides links to the synthesized RTL. So if we want to look at the C++ and the RTL side by side, we can switch to our RTL versus C++ perspective. Open up our RTL.v file and drag it so that it is next to the source editor. And now, when we start clicking through the other views, not only do we see the highlighting of our C++ source, but we see highlighting within the RTL source as well. So as I select the multiplier in my RTL schematic, I now see a star selected in my RTL that corresponds to the same star from our C code. Going back to our top level design, we can then click through some of the other objects. So here, for example, is an adder in my RTL schematic, which is now highlighting an adder in my RTL file, which is also highlighting an adder in our C source. So now it is very easy to relate our C source to the synthesized design. This concludes the introduction to Design Analyzer.